ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in our last discussion, we introduced you to the concept of high speed devices, some of the basic aspects. Particularly, we discussed the how silicon is all pervasive, that is one thing that we saw. Then we took up what are the basic characteristics of devices which decide the high frequency performance. I will just go through briefly some of those things which we discussed towards the end of our discussion, because I might have rushed in a bit. Now, I have given the title for this second lecture as requirements for high speed circuits and devices and materials. So, let us just go through quickly what we did last time. We saw what is meant by the cutoff frequency of the MOSFET. We discussed the characteristic frequencies. There are two. One is the cutoff frequency, other one is the transit frequency. And the cutoff frequency we discussed with respect to the equivalent circuit of the device. R is a resistance which comes externally to the device. It can be the resistance of the gate, or it can be the on resistance of the previous device which drives the transistor, and this is the gate capacitance Ci. So, we have seen in detail that I do not let you not go through that, you can easily work it out also. The cutoff frequency of this device is the frequency at which the power gain falls to half, output power falls half, that is the 3 dB point, that is 2 pi RC is the frequency. Okay. Now, the transit time, other parameter that we were discussing was the transit time. Now, the transit time is defined as the length divided by velocity. We have also gone through this in detail. Now, it so turns out that the velocity is proportional to the electric field, okay, product of mobility and electric field, and electric field is drain to source voltage by the length, and that electric field is actually the voltage drop across the channel divided by the length. So, that is the electric field, and when you substitute all these together, transit time is actually equal to length square divided by mobility and a voltage dependent term. So, you can see that it is very important to reduce the channel length to have smaller transit times, because the transit time actually decides what is the cutoff, what is the transit frequencies, okay. And the transit frequency is actually the frequency at which the output current to the input current becomes equal to 1. That we saw yesterday, we derived it with respect to the equivalent circuit. So, you can see here the transit frequency f t into 2 pi, that is omega t, is defined as 1 by tau t transit time, that becomes ultimately equal to Gm by Ci. So, what we are saying is you need to have, if you want to keep this omega t or the transit frequency high, you need to keep the transit time low, which actually can be achieved by reducing the channel length and also having high mobility. That all we saw last time. And in terms of the parameters for the circuit engineer, you can say the Gm, transconductance, must be high, and the capacitance associated with the device, including the stray capacitance, must be low. Now, what we saw in that series, that resistance R which was coming at the input, which decides the cutoff frequency, is actually the on resistance of the previous device. So, now tell you what is on resistance, I have put this diagram. here this is the output characteristics, one characteristics of the MOSFET for a given, for one voltage Vg gate to source voltage. Okay. So, here you can see this curve is linear in the initial portion, and that linear portion has a slope which is actually delta Vd by delta Id. Okay. That is the volt resistance. So, this change in voltage divided by change in current, which actually the inverse slope of this, that is actually the on resistance. The resistance of the device when it is just in the on state. Okay. That is actually what we are saying here. So, this on resistance, on what does it depend? We want to keep it minimum. Any resistance, any capacitance should be kept to a minimum. So, we want to keep the resistance to a minimum. That means the slope should be, it should be as steep as possible. It should be as steep as possible here. So, it is governed by certain equations of the MOSFET. This portion of the MOSFET characteristics is called the linear region. To go out here, it is called the saturation region on this portion. So, in the linear region, the ID is related to VDS and the gate voltage by this particular relationship. Okay. ID is equal to some constant which depends upon the mobility, gate oxide, channel width and channel length. Notice everywhere these two terms, the channel length and the mobility, will haunt the speed of the device. It is the one which troubles the speed of the device, because that is the one which controls the cutoff frequency of the device through this on resistance. So, this is the well known equation. ID is linearly related to VDS in this portion. Okay. For a given, if you increase VGS, this quantity, if you increase, that becomes less, ID becomes more. That means VDS divided by ID becomes this quantity, or delta VDS by delta ID is actually this quantity. I am just putting it, you differentiate it. So, instead of putting delta ID by delta VDS, I am putting delta VDS by delta ID. Okay. That is the resistance, and that resistance is inverse of this quantity, which actually is proportional to length, inversely proportional to mobility. Very clearly, you must reduce the channel length, and also you must have device mobility or carrier mobility should be high. Okay. Other parameters of course are the oxide capacitance and all. It goes without telling that those should be small, those should be larger, but you can't tolerate large oxide capacitances. So, do not try to maximize oxide capacitance, maximize this quantity, maybe this voltage can be increased. There also there is upper limit to the VGS. What is the upper limit? Supply voltage. If you are using just 1 or 2 volts, VGS will be just 1 or 2 volts, and VTN is the threshold voltage. So, ultimately what we are telling is small values of L and large values of mobility, N, keep R on low. That is the key to the success of achieving higher speeds. Okay. So, you can get higher cutoff frequencies and also higher switching speeds, because when R is small, the charging time is small, faster charging. Okay. That is about the on resistance. So, the high speed circuits ultimately need devices with high transconductance, low on resistance, devices with high transconductance, or ultimately you are looking for high transconductance, low on resistance, and of course, high cutoff frequency, high transit frequency omega t and high cutoff frequency. All these can be achieved by tailoring the parameters, the key parameters, the channel length and mobility. Increase the mobility, reduce the channel length. That is what we saw just now. So, carrier mobility, which governs the velocity, should be high for achieving all these things. Capacitances should be low, because after all this quantity, that is the cutoff frequency is Gm by C. Okay. So, you need to keep the capacitance low, so that cutoff frequency is high. Okay. R on also, R must also be kept low. Okay. So, these are some of the key things that we look forward to in the high speed circuits. And when you say mobility, you want to keep it high, that we saw from our previous slides. What is this mobility? Mobility is actually a proportionality constant which decides what is the velocity for a given electric field. Now, this mobility depends upon doping and also temperature. So, this actually, please remember these two graphs. Later on we may have occasion to recall this. Okay. So, the doping affects the mobility once the doping concentration is somewhere around 5 times 10 to the power 16. Till that time, the mobility in silicon, what I put is the mobility of silicon, because we are talking of silicon at the time being, that mobility is constant for the electrons, that is about 1500 centimeter square per volt second. But once you go down to doping concentrations which are 10 to the power 17, 18, etc., which you may not like to do because mobility will fall. Okay. And this mobility fall is due to what is due to the scattering of the carriers by those impurities, ionized impurities. Because more the carriers are there, more the dopants are there, those dopants prevent the electrons from moving smoothly. They get knocked or they get scattered by these impurities. That is why when the doping becomes high, scattering becomes more, the velocities fall. Now, this particular value of 1500 that we have put here, that is the mobility at room temperature. So, if I take a look at the mobility, total temperature dependence of mobility, a qualitative picture I have drawn here. Lower temperature mobility will be low, decided by this graph, this plot, mu I. There are two graphs which I have plotted. One is going up, that is mobility mu I, which is ionized impurity scattering, that keeps on increasing with temperature. That is because if the temperature is higher, okay, the electrons have energy to move faster and they do not get bothered by the scattering of these ionized impurities. Higher the temperature, less is the scattering, so we get higher mobility. That is what is shown here. That is one mechanism of scattering. There is another scattering mechanism which I put by this line, that is mu L, that is called lattice scattering mobility. I am just touching upon some of these things, though it might have been discussed in somewhere else in some other basic courses in circuits and also in devices, but this is necessary to have some idea of the parameter variation with temperature. That is why I am just touching upon this. This lattice scattering mobility keeps on falling with temperature. This is because scattering increases if the temperature increases, scattering by these lattice atoms. What is that due to? When the temperature increases, the lattice atoms vibrate more and more. If they vibrate more and more, when an electron comes like this, you can see it gets scattered more and more. If the temperature is small, the vibration is less, therefore the scattering is less. So, when the scattering is less, the lattice scattering mobility is high. When you go to higher temperature, it falls. So, you can see the combined effect of scattering from the ionized impurities, because that scattering is electrostatic scattering, charged ions which deflect the electrons. This is actually due to the vibration of the atoms. The vibration depends upon temperature. The electrostatic scattering reduces with temperature because electron has got better velocity. Those two combined effects give the mobility variation, increasing initially governed by ionized impurity scattering, then falling decided by lattice scattering. Okay. Now, the total effect, the effective value is actually just like putting two resistors in parallel, 1 by R is equal to 1 by R1 plus 1 by R2. It is equivalent of that. So, let us not get into the derivation of this, but the implication is the effective mobility is governed by these two equations. Finally, this is a variation. So, if you go to lower temperatures, there is a chance for you, please remember, because we will be evoking this concept later, there is a chance for you to have higher mobility, that is higher velocity for a given material, provided there are no ions which are scattering. In other words, in the path in which the electrons are moving, there should not be ionized impurities. So, if you can separate out the ionized impurities and these electrons, then there is no ionized impurity scattering. That means, this term is not there. Entire mobility versus temperature curve will be like this, totally like this. If that is the situation, you go down to lower temperature, mobility can be high. Okay. So, this is one concept, please remember. Later on we will see, when you go to high electron mobility transistors with gallium arsenide, those devices depend upon this property. In the sense, there is the ionized impurities and electrons are not in contact with each other. There are two regions which are created which separate them out. Still, there are enough electrons, but the dopants which supply those electrons are kept in some other region. They are isolated from each other. So, that way you can make use of this thing. In fact, that is what we want to discuss later on when we come to gallium arsenide devices. So, some idea of this temperature dependence, the lattice scattering mobility is T to the power minus 3 by 2, ionized impurity scattering is T to the power 3 by 2. There are of course slight variations in that parameter here, it is T to the power plus n, and you can call other one as T to the power minus n. The other thing that we will have to be concerned is the mobility is not so much dependent on frequency, okay, because in the frequency that we talk of, they do not vary. They are dependent on field, okay, and temperature. If you have go to very high fields, they will be changing. Otherwise, with field it does not change. Okay, I am sorry, with frequency it does not change. That is a constant. In fact, even at high frequency they use that concept. Okay, constant mobility. Because all those equations that one develops is based on the constant mobility with frequency. Okay. Now, the capacitances. You never like the capacitance to be large at the input side from the point of view of the cutoff frequency. Okay. That should be kept low to bring down the, to increase the cutoff frequency and bring down the switching speed. In fact, when I say bring down, it will improve the FC. Okay. Floating capacitance. Okay, you must reduce the capacitance to improve the cutoff frequency. What I have written here is the routing capacitance or the routing capacitance will add to the input capacitances and will bring down the frequency and also hurt the switching speed. That is what I have written here. Now, solution for that is, the solution is reduce those stray capacitances. For example, when you have a silicon wafer on which you have a wire running, okay, then there is a capacitance of this wire with respect to substrate. Now, usually that capacitance is large because it runs on a thin oxide on the semiconductor. So, all through the length you have the capacitance like a transmission line, you have the capacitance coming up. Now, if I increase that insulating layer, or okay, if I use a substrate which is actually a silicon on an insulator, okay, you have a substrate which is totally insulating material and a silicon layer is there, then when you run the capacitor, the wire here, the capacitance of the wire with respect to that insulating substrate, a thick substrate, that will be small, because after all capacitance is proportional to area, but if the thickness is more, capacitance reduces. Okay. So, thickness is more because that insulating layer present. Okay. That is why the capacitance is small. Plus, usually it will be capacitance of this silicon layer. If it is coming, you will have epsilon r, which is 12. If it is insulating layer, which is epsilon r is smaller, like oxide, then the capacitance is automatically small. So, what I am trying to point out is, we will have occasion to discuss more about this later. You can reduce this capacitance if you use an approach where semiconductor on insulator, like silicon on sapphire. Sapphire is insulator, a thin layer of silicon which you use for making the MOSFET. Okay. Then run the wire across on the top of that on oxide, then the capacitance is small. I will illustrate more of this later on when we discuss more of gallium arsenide based devices. The other thing is, instead of sapphire, just an insulating layer, that is SiO2 itself is okay. We will see when you go to gallium arsenide, you do not have to worry about sapphire or insulator. Materials like gallium arsenide themselves can be very high resistivity materials. You call it as semi insulating material. Okay. Instead of insulating material, semi insulating. Insulator will have resistivity of about 10 to the power 13, 10 to the power 14 ohm centimeter. Semi insulating material will have about 10 to the power 10, 10 to the power 9, which is much higher compared to a semiconductor. So, those concepts, in fact, I am just giving you only a flavor today on this. More about this we will have occasion to discuss. Okay. So, the concept is not only increase the mobility by, if possible, by going to lower temperatures, or we may have to change the material, okay, and use also small channel lengths, which will increase the velocities and also transconductance. The other thing is reduce the capacitances by reducing the stray capacitances, the capacitance of the routing capacitance with respect to substrate by using insulating substrates. Those are the concepts which are important here. So, that means, to reiterate what we are telling, the requirements for high speed devices, small transit times, I have said it more than once, but put it in black and white here, or in color, white and black, white and blue, short channel lengths and high carrier mobility and velocity. Okay. So, if you now, what we said is short channel lengths and other one is mobility. These are the two things one has to remember throughout to get to higher speed. Short channel lengths, how to achieve? That is put here. The short channel lengths are achieved by lithography. After all, you keep the source and drain at certain distance. Okay? So, when you do that, that gap which you decide is for example, what we are talking of is, if I take the substrate silicon for example, p type silicon, if I take, okay, and I have this oxide which defines the active region of the MOSFET, and then you have this oxide which will form the gate oxide, and then on the top of that you will have polysilicon deposited or a metal deposited for example, and then you define this region. Okay. That is the channel length. This is the channel length. Okay. Because once you do that, afterwards you can define your source and you can define your drain by introducing impurities through this. We can implant it through this oxide. Okay. To take contact, of course, you have to open the windows and all. Now, what I am trying to point out is, this is that L that we are talking of right through, that is the channel length. That is the channel length. You want to keep that minimum, and the electrons actually will be transported through this layer. You want to keep the mobility high in that layer. Okay. So, this channel length is decided by, can make it smaller and smaller. What is the limit? Limit is how small length you can etch, and that is decided by mobility. So, mobility of the lithography, okay. The mobility, the lithography decides this length, photolithography. So, the ultimate limit is lithography, that is what people are talking of now. You can go down to 0.1 micron, that is the technology today. So, if you have to get down to 0.1 micron, it is very difficult. In India, we do not have 0.1 micron technology today. What we have is, we can define channel lengths in semiconductor complex, I think about 0.8 microns. So, we are far lagging, because when you go down to smaller and smaller channel length, smaller or better and better lithography, the technology is more and more complicated. It gets more and more costly. Okay. So, if you can handle this problem with longer channel lengths, still have higher transit times, you are in business. Okay. So, I hope this point is clear. This is what we are trying to reduce, which is decided by the gate length, which you decide by lithography. So, photolithography, that is what I mean by saying smaller channels are achieved by lithography. Let us go back to that one. This is actually a diagram which I deliberately put, okay, which shows the cutoff frequency which has been achieved. These points are actually the measured cutoff frequencies with silicon MOSFET, and this is of course the estimated cutoff frequency. You can see on the x axis we have the channel length L, on the y axis we have the cutoff frequency Ft or Fc, what we are calling. Okay. So, you can see here, if I go from 0.1 micron, 1 micron, 5 micron, nobody talks of these days, except maybe in some academic institutions where they want to try out some things. Even in our laboratory we have 1 micron technology. Okay. So, you can see for 1 micron you can get about 2 to 3 gigahertz, and when you go down to 0.1 micron, which Intel is boasting of, 10, 20, 30 gigahertz is the cutoff frequency. That is how they are able to make this Pentium and all with frequencies which are in few gigahertz range, by reducing the channel length. So, in silicon you get this entire curve by varying the channel length by lithography, totally controlled by lithography. Now, you can see if I have an alternate material, okay, we will see how it is later on, we will see, but you can see this particular diagram here, this graph, all these open circles, that one the cutoff frequencies are higher than silicon. For example, you can see what you get with 1 micron with this gallium arsenide based field effect transistor, that is here, that is something like 12 megahertz or something like 10 to 15 megahertz range, I am sorry, gigahertz range, megahertz nobody talks of these days. So, gigahertz range, same thing if you want to achieve with silicon devices, you have to go down to smaller channel lengths, at least about 0.3 microns. If you go, you can get what you can get with gallium arsenide 1 micron. What you are telling is, why I am not telling you right now, I am just giving you the result in the head. You change your material from silicon to a material like gallium arsenide and make field effect transistor there, you can get higher speeds with longer channel length. What is the advantage? The advantage is the constraint that you are putting on here to achieve 0.1 micron technology is relaxed. You can go to 1 micron, and 1 micron a laboratory which does not have that extra facility can accommodate. Okay. So, that is what I am trying to point out here. You can go and have a longer channel length and get much higher cutoff frequency for same channel length, or a cutoff frequency which you can achieve with much smaller channel length. Okay. To put it simply, the entire curve gets shifted up. What is the reason? Reason is the different material. What we said just now is smaller lengths you can achieve, you can achieve it by lithography. But if you do not have that lithography, you can go to higher velocities, or even if you have that lithography, you can go to higher velocities, which is achieved by using alternate materials with high mobility. So, it is L by mu ratio always. L should be reduced, mu should be increased. Okay. So, if I keep same L, if I increase the mobility, I get higher frequency. That is the idea. Okay. Now, velocity is of course mobility in direct equation. So, I hope that is understood now. These are some of the curves you can see. Then you can see there are curves are keeping on shifting up. Silicon MOSFET, then above that you have got gallium arsenide MOSFET, then above that you have got aluminum gallium arsenide MODFET, okay, and above that you have got another material. Okay. Please do not worry about these terminologies, looks like a big jargon, but notice one thing, this curve is even above this curve. That is, this is based on gallium arsenide material, where higher mobility is there. The next curve on the top is based on another device consisting of gallium arsenide and aluminum gallium arsenide. In fact, this is where the trick is done, the trick that I was mentioning. Separate the electrons from the dopants. Okay. Electrons are confined to this gallium arsenide layer and the dopants are confined to the aluminum gallium arsenide layer, a ternary compound. What it is we will see later, but two different materials. So, electrons are confined to that high mobility region. So, the ionized impurity scattering is removed from the picture or reduced. Okay. And here if you go to lower temperatures, you can get this curve up even further, because if you remember we plotted the temperature versus mobility like that, and you had this curve here, this curve. I am removing that. That is the lattice scattering mobility. By separating the donor from the electrons, then the whole thing is like this. If I go down to temperature, you can get, you will not believe the mobilities of thousands, tens of thousands you can get from 1000 or 100,000 you can get if you go to liquid nitrogen temperature. No doubt at that point you have to worry yourself. In silicon you can't do that, because in silicon when you go to lower temperature and if you separate those electrons from donors, you may have advantage, but still in silicon there is one problem. You will see that carriers get frozen, carriers are not available for conduction. Where do you talk of mobility if there are no electrons which are moving? Okay. They are frozen, you freeze them, whereas if you go to materials like gallium arsenide, you will see there is no freezing effect. So, carriers are available, you can separate from the donors and you can go right up to this curve here to get better mobility. So, these are some of the benefits that you can get by switching over to some other material which has superior properties. Okay. So, this curve I deliberately put just to show you the improvements that you can get. You can see almost from 10, 20, 30, 40 gigahertz, go to 300 gigahertz. Okay. That is by changing the material. So, ultimately then what we see is, now you see we have come from the circuits to the devices, then from devices we found now you have to go to new materials, different materials. This is the theme of high speed circuits. Finally, okay, you have to go to better materials. So, material requirements for high speed devices and circuits. Requirement is very clear. Electron mobility and average velocity therefore should be high and should be higher than silicon. You can't buy anything which has velocity or mobility lower than that of silicon. On the same count, you cannot choose any material arbitrarily. You cannot go and say, okay, I have for example, germanium has a better mobility than silicon. silicon has an electron mobility of 1500 centimeter square per volt second, 1500. Germanium has almost double, 3000, but you do not look at germanium. Why? Band gap. The band gap is 0.72, which makes it leaky. It prevents you from operating at higher temperatures. You may ask, why do you want to operate at high temperature? After all, we are using room temperature. The devices are at room temperature. Why do you worry about high temperature? The reason is, just see the Pentium chip, how hot it becomes because of the so many hundreds of thousands of devices which are in the chip. The whole thing gets heated up. The power dissipation is so much, several watts. So, the result is the temperature rise. So, when the temperature rises, you do not want the devices lose their property. Junction should behave like junction. So, you would like to have, you can't tolerate germanium in those devices. Silicon with fan and all that you are able to tolerate. Okay. So, you are looking at materials which have band gap definitely higher than that of silicon. Higher mobility and higher. Okay. Now, you see you have got the entire range of devices. On the y axis, you have the electron mobility in at 300 degrees Kelvin. Okay. I hope it is it's a scanned one, because I thought it's better to put that, because it is something which is standard, projected everywhere. 100, 1000, 10,000, 100,000 centimeter square per volt second. You won't believe, you will not believe, unless you see this point there, which is really put, that you can have electron mobility at room temperature as much as about 80,000 centimeter square per volt second. So, you do not go and jump into that and say, I will take this indium antimonide and make use of it for making my high speed devices. Your high speed devices with that material, if it has to work, what should you do? You must cool down drastically, because at room temperature itself you will have plenty of electrons, and junction will not work like a junction. It will look like a leaky diode. So, you can't choose those materials even though mobility is high. Come down here. This is actually, please note here what I have put here in this diagram: electron mobility on the x axis, y axis, and on the x axis the band gap, minimum band gap. Just now you take it as a band gap. It is actually a band gap will be varying in certain directions. So, we are taking the minimum value of the band gap. That is, if there is electron at the conduction band, what is the energy it must lose to go to the valence band? That is the minimum energy. Okay. So, that is what is meant by, conventionally you can just say band gap, energy band gap. So, that is put here. For example, silicon, you see, it is here, that is silicon, that is arrow there showing you the silicon, and you can see the band gap is about 1.1 electron volts, and you can see the mobility is about 1500. Okay. You can see germanium band gap is 0.72 and mobility is about 3000, 3600 to be specific. So, any material which lies to the left of this curve, this vertical, this line, to the left of that line, you cannot take, because to the left of that the band gap is small. You do not like to take a look at any one of these materials, though the mobility is high. So, it is interesting that it is so turns out that all those low band gap materials have got very high mobility, but no use for microelectronics. It may be useful for some other detectors, etc. Okay. Now, IR detectors for example. Now, take a look at the material, then what we want to see is materials which are to the right side of that silicon, that is band gap higher than that of silicon. Okay. So, ultimately what turns out is you are looking at devices or materials which are above this line, horizontal line, and which are to the right side of this line, and how many are you left with? Only two of them, that is gallium arsenide with mobility which is about 8500 at room temperature, and band gap 1.43 electron volts, higher than silicon. So, we are very happy that band gap is high. So, if in silicon you can go to 150 degree centigrade, you can go to 200 degree centigrade or 250 degree centigrade. In other words, you can not merely use for high speed, you can use them also for use application in harsh environment. Harsh means high temperatures, that is one of the harsh environment. Other harsh environments are radiation environments. So, you can use them. Indium phosphide, okay, that has mobility slightly smaller than that of gallium arsenide, about 4500 electron mobility. Band gap is higher than that of silicon. So, to give you the numbers, gallium arsenide band gap is 1.43 electron volts, mobility is 8500 centimeter square per second, volt second. Indium phosphide band gap is 1.35 electron volts, band gap is 1.35 electron volts, mobility is 4500 centimeter square per volt second, that is at room temperature. Okay. Now, let us take a look at. So, we have chosen gallium arsenide and indium phosphide, which could be the potential candidates for high speed devices. These are compound semiconductors. For example, silicon and germanium are elemental, only one element. Gallium arsenide has got two elements, gallium and arsenic. Silicon is from the fourth group of the periodic table. Gallium is from the third group, arsenic is from fifth group. So, you have on either side of the fourth group gallium and arsenic. When you alloy them together, single crystal material, you get gallium arsenide. So, that is called gallium from third group, arsenic from the fifth group. Sometimes you call it as 3,5 compound, 3,5, 3 third group, 5 fifth group. So, gallium arsenide is a 3,5 compound semiconductor. What about indium phosphide? Indium phosphide is also 3,5, indium from third group, phosphorus from the fifth group. So, we are looking at 3,5 compound semiconductors. What are these things? Indium antimonide, indium arsenide, etc. are all these are 3,5. So, they are all third group and fifth group. And if you take a look at cadmium telluride, that is also a compound semiconductor. It is not 3,5, it is 2,6 compound. Cadmium belongs to second group of the periodic table, tellurium belongs to the sixth group, 2,6. So, similarly, your zinc telluride, zinc sulphide, etc. belonging to 2,6 compounds. You can also have, so now we have said 3 elemental in the fourth group, silicon germanium, 3,5 gallium arsenide, indium phosphide, gallium antimonide, indium arsenide, indium phosphide, all those 3,5, 2,6 zinc sulphide, cadmium telluride, cadmium sulphide, all this 2,6. Okay. So, you can see it opens up the entire galaxy of materials by mixing two elements from the second group, sixth group, third group, fifth group. Okay. You have left out one thing. What about mix two from the same element, same group? For example, you can take silicon and carbon, silicon carbide. That is what? Both from fourth group, you call 4,4 compound. Silicon germanium, we hear so much about silicon germanium. Both are fourth group, it is an alloy, it is a compound semiconductor. So, when you say compound semiconductor, you must remember you are saying a word, it is like a mantra, it contains so much, it is like saying Om. Okay, it contains so much rich information when you say things like compound semiconductor. And when you say compound semiconductor, you also talk of these are only binaries, 2 elements. You can mix 3, 4, you can see it is a wide open domain. We will see more about that subsequently. So, you have much more flexibility. Now, we have said about electron mobility. I have been silent about the whole mobility. I have been silent because it does not look attractive. You can see here silicon for example is there, hole mobility is about 500, 2, 3, about 400, 450, hole mobility for silicon is that. But if you see gallium arsenide, it is lower or almost same. Indium phosphide, it is even lower. So, you see, you jumped up with joy when you saw the gallium arsenide having electron mobility much higher than that of silicon, but you look up the hole mobility, it is way down. So, do you throw this material out? You do not. You make devices which depend only on electron. Do not make devices which depend upon the hole transport. So, avoid making devices which depend upon the transport of charges involving holes. Make devices which involve for transport of electrons. So, that means you are in business. That is why I just put this diagram to tell you that do not think of making of CMOS with gallium arsenide, because you can have n channel devices, no p channel devices. Okay, this is just a diagram which looks a bit complicated. Okay, if you go back to these curves, you will see all these, some of these are put with filled squares, squares which are dark, and some others are made, silicon, germanium and aluminum antimony, gallium phosphide, etc. are made with open squares. This is a specific thing about the material. Okay. They are termed as direct band gap materials. Wherever I have put that black or this filled square, they are called as direct band gap materials. The materials which are open here, that is the materials which have just a square without filling it in, they are called indirect band gap materials. Okay. So, the difference is, to show the difference, I have put it here. Before I go to that, I will just show this I orally said all the mobilities of gallium arsenide, band gap, indium phosphide, electron mobility, etc. I have already told you. So, let us go back to this now to see what is the meaning of direct band gap and what is the meaning of indirect band gap. This looks horrifying, this diagram, but do not worry about that. All that you have to take a look at is, for example, if I take this material here, let us see, let us take a look at gallium arsenide. The gallium arsenide, these are the energy versus momentum graphs for different states of the electrons. So, the energy versus momentum graph in the valence band, that valence band means you understand, conduction band means you understand. Within the valence band, how the energy varies, energy versus momentum varies, that is that bottom curve here. Okay. This graph here, this is the valence band. Okay. The energy of the electron varies like this. Do not worry about the other lines, because those are the electrons usually, I am sorry, the holes usually in the valence band occupy the highest energy position. The electrons in the conduction band occupy lowest energy position. So, this is the way the energy versus momentum will vary in the conduction band, and the lowest energy position is this. Okay. So, normally when you plot the energy versus energy band diagram, you plot it like this: conduction band, valence band. Okay. You plot it like that, and this is of course the conduction band here and the valence band here. What is plotted there, here, from here to here, is in this region, and what is plotted here below is in that region. We do not have to worry of 101 lines. In fact, I need not even have shown that. I can just say, in the case of gallium arsenide, that curve, the energy versus momentum energy versus momentum, okay. I show only one curve. So, what is important is where the tip is, okay, because the holes will tend to occupy this position, top of the valence band. So, the tip of that you plot as the valence band top. Okay. Here, so this is the curve that I am plotting, this portion only, that is what matters. And in the conduction band, this is the portion. So, that portion is like this, exactly above that, like that. That is the energy versus momentum, or K. So, what we are telling is, this is actually a simplified representation of the energy band diagram. This is what is within the energy band diagram. Electrons will be occupying this position or this position like that, but generally they will all be here, and generally the holes will be here. Any transition here will be from here to here. Losing that energy, it can just move down to the valence band. So, a direct transition is possible. That is why in cases where the minimum of the conduction band here is directly above the maximum of the valence band, such materials are called direct band gap materials. Okay? And any transition of electrons from here to here just will be accompanied by emission of light, because okay, it is only the energy conservation that has to be taken into account. These are used for photonic applications, direct band gap materials. For microelectronics application, it does not really matter whether it is direct band gap or indirect band gap. Those who talk of photonics, they will say, I am interested in direct band gap material. Whereas, if you take say indium phosphide for example, minimum there, maximum here. So, this also has same value. So, the gap here from here to here, what is that? That is the Eg. That is the Eg. Similar diagram for indium phosphide, only difference is this is smaller. For gallium arsenide, this is 1.43 electron volts for gallium arsenide. For indium phosphide, that is Eg is 1.35 electron volts. Okay. So, that is the situation here. Now, you take a look at silicon, this diagram. See, this diagram comes like this from that edge, this goes up like this. So, for silicon, the diagram is silicon and germanium for example, you can see that it goes up like this in the conduction band. This is the conduction band minimum, because the electrons will go and occupy the lowest position in the energy. So, that is the conduction band minimum. And if you take the valence band, you can see that okay, that is the EC. If you take the valence band minimum EV, the variation is something like this. Okay. We are not bothered about other regions, do not worry about other lines, only one line. This is the highest position for where the holes will be occupying, and this is the lowest position where electrons will be occupying, and this is the energy and this is the momentum. Notice the electron here, when if it has to make a transition from the conduction band edge to the valence band edge, okay, it will have to satisfy energy conservation. It should look for a particle which will absorb the energy. It should also look for a particle which will absorb that difference in the momentum. That makes the transition difficult. As a result, the transitions directly from here to here do not take place. They will take place in two steps. That is, they will move down to one level here like this, then like that. And in this one level, they will just change their momentum and then make a transition. So, this is like a half step jump. Okay. Instead of one high jump here, this is half step jump. Okay. So, here let us suppose an example, here the result is the transition is not taking place directly from here to here, the transition is taking place indirectly through another intermediate level. That is why it is called as indirect band gap semiconductor. So, you have got direct band gap, and indirect band gap. Okay? Direct band gap and indirect band gap materials. Okay? Direct, indirect band gap. This is gallium arsenide, indium phosphide, this is silicon and germanium. Okay. So, you have got two varieties, that is what I depicted there when we showed it. We do not get into the physics of how it happens, direct or indirect band gap, it so turns out that. So, I will actually ultimately what we are telling is you can use gallium arsenide for applications in microelectronics because of this property, high mobility which is actually higher than that of silicon and band gap which is higher than that of silicon. Similarly, indium phosphide which has got higher mobility, electron mobility 3 times that of silicon and also higher band gap. All these things make it very useful, very attractive for high speed devices. In fact, they are being made in India. Hyderabad, Catech company makes, as I said earlier, MMICs, monolithic micro integrated circuits with gigahertz frequency range, they are making that. Okay. So, it is not it's not a myth, it is a reality. The high speed devices, okay, this mainly for defense applications. So, with that I stop today's lecture, we will discuss next time further about these things. Okay.